Hi, I'm Kishan Jeeveswaran and today I'm proud to present our paper titled Gradual Divergence for Seamless Adaptation, a novel domain incremental learning method. Our work mainly tackles domain incremental learning, which is a subset of continual learning that addresses the challenge of acquiring knowledge from new domains or tasks in an incremental manner. One of the major challenges in learning new domains is called catastrophic forgetting, and it's a phenomenon wherein the network forgets information about previous tasks. This is caused by the information from the new domains overwriting the network weights corresponding to the information of old domains or tasks. Though different approaches like experience replay, regularization, and architecture expansion have been proposed to mitigate catastrophic forgetting, they don't explicitly address representation drift caused by the weight updates. Representation drifts are severe at task boundaries, and they are caused by the disruption of clustered representations corresponding to previously learned tasks while learning a new domain or task. Representation drift is directly correlated with performance drop on old tasks and contributes significantly to catastrophic forgetting, and it remains unexplored in the domain incremental learning literature. To address this, we suggest a three-stage training process to gradually adapt the learning model to new domain sample representations, thus reducing the drift of representations across tasks. Out of all the approaches in the literature, experience replay has been shown to effectively mitigate catastrophic forgetting. However, it lacks a mechanism to explicitly address drift in representations at task boundaries. We adopt a two-classifier architecture which learns on the first task similar to other experience replay methods using cross-entropy loss and consistency loss on predicted logics. Experience replay methods often employ a constant memory buffer, and the consistency loss is applied on the buffer samples. Our method, dubbed DARE, proposes a novel three-stage training process: divergence, adaptation, and refinement, to adapt the representations of new domain samples into the feature space spanned by the old domains while learning new domains. This effectively reduces the representation drift at task boundaries, as it preserves representations of old tasks while adapting the information of new tasks according to them rather than vice versa. The divergence stage aims to tighten the decision boundaries of the two classifiers around the representation space spanned by the samples of already learned tasks. This involves maximizing the divergence between the two classifiers while keeping the weights of the encoder frozen. Then, the adaptation stage aims to adapt the encoder G so that the representations of the new task samples are adapted within the subspace spanned by the already learned representations of previous tasks. The goal is to learn a consolidated representation space that supports the subsamples of new tasks which remaining close to the optimal representations for the previously learned tasks. This is achieved by freezing the classifiers and adapting the encoder to minimize the discrepancy between the logics predicted by the classifiers. The third stage, called refinement, aims to refine the encoder and classifiers to effectively consolidate the new task information with the previously learned knowledge such that the consolidated representation space and decision boundary perform well on all the tasks. This stage employs a cross-entropy loss on the new task samples and consistency loss on the buffered samples, similar to task 1. We iterate through the three stages multiple times while learning each task to consolidate the information in a structured manner within the network weights. Experience replay methods use a constant memory buffer to store representative samples from all tasks to replay while learning new tasks. Reservoir sampling is a popular strategy to sample data points from tasks using a uniform distribution to store them in the memory buffer. There is a non-trivial probability that logics are stored in the buffer at the very beginning or end of learning a task, leading to suboptimal performance. To improve this, we propose the intermediary reservoir sampling or IRS strategy, which employs a normal distribution over the learning trajectory of each task to sample the data. The mean of the distribution is set to the intermediate stages and the buffer is populated accordingly. This encourages the storage of logics with more dark knowledge about the current task, which in turn propagates the knowledge across future tasks through distillation resulted by the consistency loss. Moving on to the experimental results, We chose two domain incremental learning benchmarks, DN4IL and ICPAR20, and we report different performance metrics around 3 different buffer sizes. It is worth noting that we perform experiments under extremely small buffer settings, which is ideal for real-world applications. As can be seen in the table, DEA achieves consistent improvements in last accuracy and backward transfer across different buffer sizes. Another variant of our proposed approach, dubbed DEA++, maintains an exponential moving average of the learning model, and it is more memory efficient than CLSER and DUCA while being competitive in performance. We also find DEA and DEA++ outperforming their counterparts with smaller buffer sizes. Specifically, DEA learned with buffer sizes 50 and 100 outperform DER++ learned with buffer sizes 100 and 200 respectively. An analysis on the proposed buffer sampling strategy shows that it achieves better last accuracy and backward transfer compared to the reservoir sampling strategy. Storing the samples in the intermediate stages helps the memory buffer store more information about the task being learned, and replaying samples stored in such manner helps the model consolidate more knowledge about old tasks. Analyzing the change in the representations of past tasks will shed some light on the amount of catastrophic forgetting in the neural network. We analyzed the representation drift of early task samples in 2 ways. First, we plot the accuracy of the task 1 validation set over the course of training in the other domains. This represents the disruptive nature of the representation drift at task boundaries and their detrimental effect on the accuracy of the seen tasks. It can be seen from the figure on the left that both ER and DR++ undergo a significant decrease in performance for task 1 samples at the beginning of learning task 2. The same behavior is observed at the beginning of tasks 3, 5, and 6. However, DEA prevents such loss in accuracy for task 1 samples while learning new tasks. Second, we examine the iteration-wise representation drift of the buffered samples in the figure on the right. The plot reveals that buffered sample representations experience a sudden shift at task boundaries, indicated by the alternating shaded regions. However, DEA doesn't exhibit a comparable representation change as we adjust future task representations into the initial task representation space. The drift is minimal and gradual. Task recency bias is an important concern in control learning, wherein the model predictions are biased more towards recent tasks and result in more forgetting for earlier task samples. In domain incremental learning, task recency bias can have severe consequences, particularly in safety-critical applications like autonomous driving. Although task recency bias has been extensively studied in class incremental learning and is straightforward to analyze as classes are distinct between the different tasks, it has not been widely studied in the domain incremental learning scenario due to its inherent aspect where all tasks share the same set of classes. As a step forward in studying this bias in domain incremental learning, we analyze the logit norms of different approaches. DNNs that predict logits with a larger magnitude or norm directly translate into overconfident predictions, which in turn can indicate the bias of the model toward samples belonging to a certain task. Figure on the left illustrates the logit norms predicted by the different CL models on the first and last domain samples. While ER and DR++ are more confident on the last task samples compared to the samples belonging to the first task, DEA achieves more uniformly distributed confidence over old and new task samples. Additionally, figure on the right illustrates the calibration error of the model on the initial, last, and old task samples. It is further evident that DEA achieves a low calibration error compared to other CL methods. Concluding the presentation, we proposed a novel method to address representation drift in domain incremental learning. Our proposed method, dubbed DEA, minimizes representation drift at task boundaries and effectively assimilates new domain information into the featured space of old task samples. The inclusion of an effective buffer sampling strategy allows the preservation of the dark knowledge learned on old tasks while learning new ones. Our empirical evaluation shows that DEA outperforms existing methods across different domain incremental learning benchmarks and less forgetting and improved performance on seen domains. Furthermore, DEA exhibits efficient memory and computational usage, reduces bias towards recent task samples, and inhibits abrupt representation drift at task boundaries. These results demonstrate DEA's efficacy and the potential for practical applications in controller learning. Thank you to the ICML organizers for providing me with the opportunity to present my paper. I also want to express my gratitude to my co-authors and supervisors, Ilahi Arani and Bahram Zunus, for their invaluable contributions to this research. Thank you all for your attention.